All right, good morning, chemists. We'll get started now. We're going to jump right into chapter 16 and continue talking about acids and bases and pH calculations. If anything, we're going to continue practicing, that magic square. If you know one corner, you know all of it, but with weak acids and weak bases. And that's going to be for like the first 60 minutes of class, and then the last 20 minutes we'll start midterm 2 review because our midterm is on Tuesday. And last time when I did the review, I saw a lot of you like taking pictures of the screen and stuff. So I just went ahead and put together the document that I'm going to work through that covers chapters 14, 15, and 16. It's right here, but we'll do that at the last like 20 minutes of class. All right. And then we'll do the same thing on Thursday. So like first half like class, and then last 20 minutes is review. Yeah. What did I say? Well, today's Tuesday. Yes, it is on Friday in recitation. Yes, sorry, I misspoke. Yes, it is on Friday in recitation like typical. And actually what was in my mind is that my review session is tonight at 5:30 in this room. So the time is a little bit different because I think there's a physics exam in here that night. So let's not be there. So it is tonight at 5:30. There's a page on our Carmen modules with the activity, the Zoom link, everything. You'll find the recording on that page sometime tonight. All right, so let's get back into acids and bases, and then we'll do review, and then finally I can sit. So I don't know if you've noticed, I always stand when I teach, except when I review. When I review, I allow myself to sit down. Okay. So let's jump back into this and talk about acids. Right, so we did an example just like this one on Thursday. We calculated the pH of a weak acid, acetic acid. So let's do it again, but this time for benzoic acid. So the difference here is that benzoic acid, acetic acid, those are weak acids, so we have a Ka expression we have to use. Versus what's going to be assessed on the exam on Friday, will just be strong acids, strong bases. Strong acids, strong bases, we make an assumption that all of the H plus comes from HCl. All of the H plus comes from nitric acid, or all of the hydroxide comes from sodium hydroxide. But it's different for weak acids because we have an equilibrium at play. So benzoic acid, what's the pH? So if you don't know that benzoic acid is a weak acid, here's the hint. The hint is that a Ka is given. All right, so if there's a K given, Ka meaning acid, it indicates that benzoic acid is in fact a weak acid, so it undergoes a chemical equilibrium. So I am lazy, so I'm just going to call benzoic acid HA. Is that okay? Can I just call it HA? All right. Because the idea here is any acid always has an H plus and a conjugate base attached to it. And so just calling it HA is an easier way to do that. So it looks like we're putting HA in water. This is aqueous. It undergoes equilibrium. And so we want to make sure we write a Ka expression for benzoic acid because a Ka is given. So HA, when it reacts and acts like an acid, it pops off one of its hydrogens, one of its protons, and it leaves what behind? A minus. Yeah, so that is its conjugate base, A minus. So that is a generic Ka expression. It will work with basically any weak acid. You can just call it HA. This could be HF, it could be acetic acid, it could be any one of those acids. This will work. All right, so pH, we need to calculate what is the H plus concentration at equilibrium, and then we'll negative log that number. So since we're looking for an equilibrium concentration, are we given equilibrium concentrations in this question? No, we're not. So we probably have to do what? Make an ice table. Yes. This is no different than chapter 15. Honestly, it's easier because when we plug in the numbers, let's see what happens. Okay. 0.15, that goes in the initial line. All right. Ice tables should be in molarity if it's Kc or Ka or Kb because those are all concentration. equilibriums, but your ice table can also be in pressure if you're working with gases in chapter 15. That's different than BCA tables from 1210 because those should be worked in moles. So all of these values here are molarity. All right, so given the initial conditions, which way does this reaction have to go? Forward, yeah. So minus x, plus x, plus x. Hopefully this looks familiar. And so when we add up our lines, we get there's 0.15 minus x of HA at equilibrium, x amount of H plus, and x amount of A minus. So like all ice tables, what do we do now? Put the E into the K expression, yes. So Ka for any generic acid is always products over reactants, H plus times A minus over HA. I give you the value of Ka. It's given. It's right there. It's 6 point whatever times 10 to the negative 5. All right. So I know what this value is. So let's go ahead and plug in those equilibrium concentrations into our K expression. So this simplifies to x squared over 0.15 minus x, and it is equal to 6.3 times 10 to the negative 5. Okay. Does this green equate, can we solve that? Yep. Does it require the quadratic as written? Yes. Do you want to be lazy and do an approximation? Yes. So what is the approximation we make? That minus x is really small, and we can just ignore it. So basically we're saying that 0.15 minus x is essentially the same as 0.15. It's the same number. Because we're subtracting such a small number, let's just go ahead and get rid of that minus x on the denominator so it makes it easier for us to calculate it. Now it is not a quadratic, it's simply just a algebra and a square root. All right, so to calculate x, we take that Ka value given times 0.15 and take the square root. So I get that x is equal to 0.00307 molarity. But it's molarity of what? Of what? Like, yeah, we solved for x, but what is x? H plus concentration, yes. This is my H plus concentration, and the reason I ask it is because it's not always H plus. And so we have to be cognizant of what K expression we're using, what X are we solving for, and so in this case, because we're using Ka acid, X is equal to H plus concentration. All right, so that's not our answer. We actually need the pH, so we can go ahead and negative log that number, and then hopefully we get 2.51 is what we get for our pH. All right, when you negative log that number. Okay. Quick question. You should always be asking yourself this question. The pH we just calculated is what? Acidic, basic, neutral? Acidic, great. What did we put in water? An acid, so that matches, right? Okay, good. All right, so always check yourself because if you make a mistake, that might not match up, and that's a great way to catch yourself because it gets a little bit trickier, all right? So that was the pH. It matches our intuition. Let's just be comprehensive and also calculate percent ionization. So here's the equation for percent ionization where we take the H plus concentration at equilibrium, so that's the X value we just calculated, and we divide it by our initial concentration of acid. So this case it's 0.150 times 100. So basically what we're calculating here, and so we have X, it's equal to 0.00307 over 0.515 times 100. Yeah, I guess you get like 2% or something. So the idea here, what percent ionization is, think about it. It's X over what you started with. So really what we're doing is we're thinking about, okay, how much H plus actually ionizes from our initial conditions. We put 0.15 molarity of the HA molecule in, but the reaction moves forward just enough, X amount, to make H plus. And so that's the idea here of percent ionization, how much of this HA actually ionizes. And so we get 2%. So this reaction only proceeds about 2% in the forward direction. That's a really small number. And so that's why this approximation works. So where we get rid of the minus x on the denominator, because that minus x is only worth about 2% of the overall 0.15 molarity that we see. If you remember the rules of when to use an approximation, usually the percentage you were looking for was 5%. You don't want your minus or plus x to be more than 5% of the number you're subtracting from, and so percent ionization helps us calculate that here. But I'll say for the most part in this chapter 16 that 99.9% of the time you can use an approximation in this chapter. And so we're still talking about chemical equilibrium, but like I said, it's a little easier than it was in chapter 15 because we almost always use an approximation, and all of the relationships here are one-to-one, and we'll see that. And so you'll see a lot of trends come out. All right, so there's acids. We put an acid in a water, it's acidic. So let's talk about polyprotic acids, meaning acids that can donate more than one proton. So you might be familiar with the words monoprotic acid, like HCl. All right, HCl is a monoprotic acid because once it donates one proton, it's done. It can't act acidic anymore. Sulfuric acid is not a monoprotic acid, it's a diprotic acid. So we can call that, we can simplify that as H2A if we wanted to just mean, oh, there's two acidic protons. And then finally, we can talk about H3A, a triprotic acid. All right, and from the formulas, you can clearly see how many protons are being able to be donated. All right, so here's the thing. When we're talking about mono or di or triprotic acids, those protons do not behave the same. Each of those protons have a different acidity that are dictated by different K values. So here's an example. Ascorbic acid is a diprotic acid. You can call it H2A. All right? So what we see in this table is that there is a first Ka value. That is the equilibrium to take off the first proton. But then there's another K value to indicate taking off the second proton. And so we see that Ka1 is a bigger number than Ka2. So we can say that that first proton is more acidic than the second proton, meaning that H2A much more likely to donate a proton than HA minus that second proton. All right, so you see ascorbic acid, a diprotic acid, has 2 Ka values versus something like phosphoric acid, H3A, is a triprotic acid, so it's going to have 3 Ka values. Each one is a different value indicating the strength of that acid. So you see that Ka1 is a lot larger than Ka2, which is a lot larger than Ka3. So here you see, okay, that first proton is the most acidic. That last proton is not very acidic. It's not very likely to be donated. All right, so here are the numbers. Yes, okay, each of the protons have a Ka value associated with them, but these numbers also have reactions, equilibrium associated with them. So let's make sure we can write the equation describing what Ka1, 2, and 3 is for phosphoric acid. So if you look at the table, Ka1 for phosphoric acid is 7.5 times 10 to the negative 3. But what does that number mean? Like, I know it's products over reactants, but what are the products and what are the reactants? So the idea here is we have 3 K values. Phosphoric acid is a triprotic acid. We need to take the protons off one at a time. Each K expression represents taking off one proton. So Ka1 is going to talk about and describe taking off the first proton of H3PO4, the first proton. Right? So we start with the acid, like the full acid, H3PO4. When H3PO4 acts as an acid, it pops off an H+, because that's what acids do. But what's left over? We got to be careful here with charge and number of hydrogens. What's left over? H2PO4 minus, yes. All right? So H3PO4 is our acid. What is H2PO4 minus? What is that? It's the conjugate base. Yes, it's a conjugate base. It's the conjugate base, but here's the thing. There's still protons on that. So H2PO4 minus can still act like an acid. Even though it's the conjugate base of H3PO4, let's continue thinking about this substance acting as an acid, continuing acting like donating protons. So this is what Ka2 describes. This is the number. You look it up on the table. 6.2 times 10 to the negative 8. This value represents the product in the previous reaction acting like an acid. So now we're talking about taking off the second proton. So we have to take off the first proton first. So our reactant here is H2PO4 minus. This thing can still act as an acid. So let's pop off an H plus. What's left over now? How many H's? Just one. And then PO4, what's the charge? 2 minus. Cool. So H2PO4 minus is the acid because it's doing the donating. HPO4 2 minus is its conjugate base. But here's the thing. This product we just made, can this still act like an acid? Yeah, because there's still protons left. So that is what Ka3 is. Let's take the product in the previous reaction. So HPO4 2 minus, and then this has a value 4.2 times 10 to the negative 13. Equilibrium arrow, pop off that hydrogen or that proton, and then we're left with PO4 3 minus, and that is our conjugate base in that last Ka value. Can this last product, PO4 3 minus, can that act like an acid? No, it can't. So that's why it does not have an additional Ka value. All right, let's look at that last equation. Ka3, is this a big number or a small number? Small number. Compared to all of the rest of them, it is the smallest number. So remember what a small K value means. What side of the reaction will you see more of? The product side or the reactant side? Reactants. So ask yourself, is HPO4 2 minus acidic? Is it that acidic? No, it is not very acidic because we don't make a lot of H+. If we put this into water, it's not going to produce that much H+, because Ka3 is such a tiny, 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 tiny number, right? This reaction does not proceed forward. All right, and that's what the magnitudes of these K values mean. Versus Ka1, you put this into water, you put H3PO4 into water. K is still pretty small, but it's not as small as to the negative 13. So in this case, when you put H3PO4 into water, you make a lot of H+. So therefore, this solution is fairly acidic. So those are what the magnitudes of those K values mean, all right? So it's the same idea. It's a big K value versus small K value. If you see a big K value, you make a lot of products. Your solution may be acidic if you're looking at a large Ka. All right, so those are polyprotic acids. Okay, so we talked about acids. Acids, they're easier. I don't know why. They're always easier. I think it's because we're always like breaking stuff. You're taking like HF, an acid, and you break it up into H plus and F minus, and it's super clear that, oh yeah, that H plus, that's the acidic part. That's how we calculate pH, right? I need to just figure out how much of that H plus I have. Acids tend to be simpler. To calculate the amount of H plus, we use Ka when it's a weak acid, but that's what we're talking about now, weak acids. And so these Ka values have to be given. All right, but bases, on the other hand, they follow the exact same scheme. It's just for some reason they're a little bit trickier. I think it's because it's harder to tell if something's a base, especially a weak base, because what's the giveaway something's an acid? There's an H somewhere in it. Okay, the name of it has acid in it somewhere, you know. But with bases, it's different, like ammonia. We know the Arrhenius definition of a base produces hydroxide in water. But if you look at just the ammonia formula, do you see any hydroxide? No. But like that's why it's easier for like sodium hydroxide, potassium hydroxide to tell those are bases. But those are strong bases. So it's harder to identify a weak base, and I'll show you many examples coming up here. But to remind you why ammonia is a weak base, that nitrogen has a lone pair. And what happens when you put it in water is that lone pair steals a hydrogen or a proton from water, right? So it gains a proton. It acts like a base. It's a proton, acceptor, right? And then you're left with this hydroxide, the other part of water, once you remove that proton. So we see here the hydroxide is made in this solution with water as a reactant. All right, and so when we work with weak bases, we're going to use that hydroxide concentration to calculate pH, but a little bit differently, right? Where hydroxide concentration, if you negative log that concentration, you actually calculate POH. But then you're just one step away from calculating pH. But the calculation is exactly the same, right? So there's ammonia, that's our weak base. Ammonium is our what in this reaction? Conjugate acid, yes. So you put ammonia in water, it's basic. But if you put ammonium, so NH4 plus in water, it's actually acidic. Okay, all right, there's a lot of stuff going on here, but we can still write that KB expression where we put products over reactants. Do we put water in this expression? No, we don't. So simply KB is equal to ammonium concentration at equilibrium, hydroxide concentration at equilibrium over ammonia concentration at equilibrium. Products over reactants. There we go. It's KB because ammonia is a base. For HF, will you ever find a KB for HF? Nope, because HF is a acid, so you'll find a Ka, all right? Okay, so let's do some calculations. Don't be scared, it's just like chapter 15, and it's just like those acid examples we just did, except we're using a Kb expression because ammonia is a base. All right, so we're going to use Kb. The giveaway that ammonia is a base is that I give you, so the giveaway that ammonia is a base is one, I tell you that the pH is basic, all right? And I'm asking you to calculate the Kb of ammonia. So that's the giveaway that this is a base. All right, so this first question is what I call the type 1 ice table, where you don't actually have to do a quadratic. It's where I give you initial concentrations, I give you a hint at the equilibrium line, and you calculate K. So there's another example in these slides about acids, like it was for like HF or something, but now we're just doing it for a base and calculating Kb, right? So the idea here is I measured the pH of this solution, and so that pH measurement is actually a hint to our equilibrium line in our ice table. Not directly, but it gives us a hint at the equilibrium line. So let's go ahead and write out the ice table for this reaction. And what I want to emphasize, and so I already wrote it in this question, is this expression. Ammonia is a base. We are calculating Kb. So I should write the Kb expression for ammonia. This is a Kb expression. It's ammonia plus water gives us the conjugate acid and hydroxide, right? So this is a Kb expression, and I have the formula over there on the corner. All right, so let's put in our knowns. 0.1 molarity goes in the initial line, all right, molarity. We don't care about water because it's not in the K expression. How much ammonium and hydroxide do I have initially? 0. Which way does this reaction have to go? Forward. Minus X plus X plus X. Are you sick of this yet? Then at equilibrium, what do you have? 0.1 minus X of ammonia, X amount of ammonium, X amount of hydroxide. Perfect. All right? And like all ice tables, that E line goes into our K expression. So what does this become? Kb equals X squared over 0.1 minus X. So many ice tables end up like this, X squared over initial concentration minus X, all right? But the difference here in this question is I am asking you to calculate K. In the previous example, I had you calculate equilibrium concentrations, and I gave you K. But here, I'm asking you to calculate K. It's a little bit different. So let's use the last piece of information we didn't use in this question, and that is the pH. All right? That pH is a hint at the equilibrium line. It gives us a hint into what X is, because calculating X and inserting it into this expression will allow us to calculate K. All right, so this one's different. We will not have to use an approximation in this example because we know what X is, or we will find out here soon. So I give you the pH. So if I undo that pH, right, 10 to the negative pH. All right, let me do that. So 10 to the negative, oh, actually, no, I don't want to do that. So if I do 10 to the negative pH, what concentration am I calculating? H plus concentration, right. Do I want that? Does that give me any hint to the equilibrium line? No, because X is equal to what? Hydroxide concentration. So what should I do? Am I screwed? No, all I have to do is convert that pH to POH. All right, POH, since this is at 25 degrees, I can do the minus 14 thing. All right, so I get that the POH for this solution is 2.87. If I negative log, or sorry, not negative log, 10 to the negative POH that, what concentration do I get out? I get concentration of hydroxide. Yes, is that equal to X? Yes, it is. So if you 10 to the negative pH, that is not X in this question because ammonia is a base. And if you look at the ice table, X is equal to hydroxide concentration. I don't want to stick in a H plus concentration. So that's the only difference in this question. So 10 to the negative, that number, I get that the hydroxide concentration in this solution is 0.00134 molarity. That's hydroxide concentration. This is X. Right, that's X. And since I have X, I can just plug everything into the KB expression and then go ahead and calculate KB. Should I approximate this? No, because you know what X is. If you approximate it, you're just being lazy. Yes. Because the point of the approximation is to avoid using the quadratic. Right? Since we know what X is, you just plug it in and it's just algebra. So it would be 0.00134 squared over 0.1 minus that X value there. All right? And you plug that in and you get a KB like that. All right? 1.8 times 10 to the negative 5. All right? Okay, so that's KB, yeah? Yeah, so if we don't give you a temperature, assume that it is 25 degrees Celsius. Because if we do give you a temperature other than 25, we have to give you a new KW. Because the idea here is at 25 degrees, KW is 1 times 10 to the negative 14, and that only works at 25 degrees Celsius. But like 95% of the time, we're at 25. Okay, so that's why I was allowed to, do the minus 14 thing. Like, that's why. Okay. So we did a type 1 ice table, so let's do the other kind, a type 2. All right, so let's, this time, given a K value, so I didn't give you a Ka, I'm actually giving you a Kb, but whatever. It's literally the same process. What is the pH at 25 degrees for this ammonia solution? This time I give you the Kb, so this one's different, but I still give you initial concentration, so we still have to do an ice table here, all right? So these are the questions you should ask yourself. Is ammonia an acid or a base? Because that will dictate whether you use Ka or Kb. So here, since I give you the Kb of ammonia, it's pretty clear that ammonia is in fact a base, and so we should be using the Kb expression, ammonia acting like a base. I would definitely practice writing Ka and Kb expressions because for a long time, me personally, I always thought Ka and Kb expressions were inverses of one another. They were just like opposite. That was when I was in college. Yeah, that didn't go well for me. They are in fact different. Ka is a acid acting like an acid, so donating a proton. Kb is a base accepting a proton. So it's a completely different reaction where either H plus or hydroxide is produced in the process. So anyway, that's on me, but I learned since then. So here we have our reaction. We do an ice table. 0.3 is going to go in the initial, we don't care about water, 0 of all that. Reaction has to go, yeah, I see your hands going, has to go forward, minus x, plus x, plus x. And so at equilibrium, it's 0.3 minus x of ammonia. We gain an x amount of the conjugate acid and an x amount of hydroxide. So what do we do now? E into K. So what do we get? That Kb equals x squared over 0.3 minus x. Does this look familiar? Yeah. Equals, because I gave you Kb, right? So we built the Kb expression using our ice table. Let's just set that equal to 1.8 times 10 to the negative 5, because that's what's given. All right, can we solve that for x? Yes, but it requires the quadratic. Do you want to do the quadratic? No, so what should we do? Approximate. Do you think we can approximate? Why can we get rid of that negative x? Yeah, Kb is really small. Yes, okay. So this, we don't have to approximate, it's just simply a square root. So 0.8 e negative 5 times 0.3, take the square root of that. And so I get that x is equal to 0.00232 molarity. But like I always say, once you get x, there's no meaning unless you define that variable. X is concentration of what? Is it H plus? Can I just negative log that number right away and get pH? No, this is the concentration of hydroxide because that is what the ice table says. All right, that's what the ice table says. So if I negative log this number, what am I calculating? POH, yeah, so let's go ahead and do that. Negative log that number, all right? We're getting POH is 2.63. I don't know how many sig figs, probably 2 decimal places. And then we are just a 14 away from pH, and yes, it's in the corner over there, 11.37 is our pH, all right? So the idea here is because we used Kb, we solve x the exact same way. It ends up being x squared over initial concentration when we use the approximation. But this time, x is not H plus concentration like it was in a Ka expression. It's actually hydroxide concentration. So you're literally just one step away from getting pH. It's no different, all right? But let's check our intuition. This pH, 11, is what? Basic. What did we put in water? A base. So your brain agrees with that. Yes, and you're satisfied and we can move on. Okay, good. Good, because let's say this is what happens a lot. Students will stop right here. A lot of students, they'll just calculate x, do negative log, and assume that's the pH. So hopefully on an exam, if you wanted to report, 2.63 is gonna be an option, all right? It's gonna be an option because that's a common mistake. But if you reported pH is 2.63, that pH is what? Acidic. What did you put in the water? A base. So that your brain hopefully doesn't like that, and you can think, maybe I should revisit this question and make sure that my answer, my work for that answer. So these are the things you want to think about. Okay, so here's the thing. In 1210, we mostly talked about ammonia being a base. Our weak base. That was like our weak base of choice. It was the only one we had you memorize. But now that we're in 1220, it's not just ammonia anymore, and we're going to learn more weak bases. And the idea here within this chapter is we're going to have you calculate pH of a lot of things. I recognize that the pH calculation isn't that hard. All right, the ice table is not that hard. Once you've done like 10 of them, you realize it's x squared over initial concentration equals something every single time. But the hard part is looking at a formula and thinking, is that an acid? Is it a base? Which Ka do I use? That's the hardest part, all right? And so here's how you identified bases. Many bases look like ammonia when you squint your eyes, all right? So many neutral substances that have a lone pair of electrons, often with a nitrogen. That's ammonia. Isn't that what ammonia sounds like? It's a nitrogen with a lone pair with some junk attached to it, right? Anything that has that is going to act like a base. So here's an example. These first four. Look, there's ammonia, nitrogen with a lone pair, junk attached to it. That's a base. It has a KB. Pyridine. There's nitrogen with a lone pair with some stuff attached to it. That's also a base. Hydroxylamine, nitrogen with a lone pair with some junk attached to it. Methylamine, nitrogen with a lone pair with some junk attached to it. All of those are bases, all right? And then they all have conjugate acids as well. That adds a layer of complexity. All right, so those are typical types of bases. What I want you to look for are things that look like ammonia. Get comfortable with ammonia. So when you see ammonia's cousin, you know, oh, I just treat it like ammonia and it's fine, all right? Because that's the hardest part. Also, other types of bases is the conjugate of a weak acid, all right? HF is a what? Acid, but F minus is its conjugate base. So if I put HF in water, the solution should become acidic. But if I just put F minus in water, that water actually becomes basic because it's a conjugate base. And so there's another idea of where bases can come from, the conjugates of weak acids. And this brings a layer of complexity to stuff, all right? And here's the last thing, all right? Like, yes, okay, ammonia is a base. Fluoride ion is a base. But here's the thing. I can't just put fluoride minus in water. I can't go to Amazon and order fluoride ion. You can't do that. You can't go to Amazon and just order sodium cation. All right, salts always come together as a charge-neutral substance. It's always sodium chloride or like calcium chloride. It's always charge-neutral. So here's the thing. It's, again, add another layer of complexity. If I wanted carbonate, the base, you're not going to find just carbonate ion. What you'll find on the shelf is actually sodium carbonate. So you have to recognize, oh, there's sodium ions that are pH neutral, and then there's also carbonate ions that are a weak base. And so that's kind of the idea we want to go with for the remainder of this chapter in identifying what are we looking at. Is it an acid? Is it a base? Which K do I use? All right, let's talk more about ammonia because this is definitely a tough one. All right, I'll remind you. Ammonia and ammonium, that is like your prototypical base conjugate acid pair, all right? If there's anything you should do, memorize these two. This is your base. When ammonia acts like a base, that lone pair grabs a proton off of water, and then you make ammonium. So these two lone pairs are now in this chemical bond on nitrogen, all right, for ammonium. So here is your base. You put ammonia in water, the solution becomes basic. But if you put ammonium, NH4 plus in water, this thing, is this a base? Nope, this is an acid. So you put this in water and it becomes acidic, yeah. So this is overall plus charge also, I'll point out. All right, so memorize those two because the rest of these base acid pairs, they all follow this same scheme. Nitrogen with some junk attached to it, and you add an extra proton to make the conjugate acid. So here's the thing. Methylamine is we start with ammonia, and we just replace one of these hydrogens with a methyl group, so CH3. Right? That's methylamine. I just replaced one of the hydrogens with ammonia. Squint in your eyes. Doesn't this look like ammonia with just like a big arm on the side? That's it. It looks like ammonia. So that means methylammonium, its conjugate acid, follows the same thing. The lone pair grabs a proton off of water, and so what methylammonium looks like is ammonium with just that CH3 there, all right? And its overall positive charge, all right? Again, squint your eyes and try to look for ammonia. All right, dimethylamine looks just like ammonia, but with just two methyl groups, so two different CH3 groups. So we're just replacing two of the hydrogens with CH3s, all right? That's a dimethylamine. That's a base. its conjugate acid is the same thing. All right, it's the same exact thing, but we replace that lone pair with a hydrogen proton instead. All right, that's what that looks like. And then finally, just for completeness, these aren't the only weak bases. I just want you to locate the trend, all right? We have nitrogen, a neutral nitrogen is a base, but its cation with an extra hydrogen is its conjugate acid. Here we have ethylamine, so it's ammonia, but just with an ethyl group on it instead, so CH3, CH2. That's the structure. And so the structure for the conjugate acid is going to look the exact same, except it has that extra proton on it. All right? So these are the formulas, all right, like the Lewis structures. And I'm trying to show you via the Lewis structures how they all look similar. But what you want to look at also is on the exam, we're not going to give you structures. We're going to give you formulas. All right? See these formulas over here? This is ammonia. If you squint your eyes, methylamine, it's just ammonia with this extra thing on it. Right? Dimethylamine looks just like ammonia with two extra things on it. Ethylamine looks just like ammonia, but like with some other stuff on it, all right? That's what you want to be looking for, because all of these are bases. All of these will have Kb values, all right? This is definitely a tough part of the chapter, students recognizing bases, things that look like ammonia, and it's tricky. I just want to expose you to all of the different bases that there are and show you that there's a lot of trends that come out here. All right, so those are bases that come from ammonia-looking things. All right, so let's talk about acid-base conjugate pairs. So ammonia is a base. Ammonium is its conjugate acid. How are those two things related? All right, so ammonia is a base. You put that into water, it becomes basic. You use a Kb value. All right. But ammonium, its conjugate acid, is an acid. So should you use a Kb value to describe an acid? No, you should use a Ka value. So yeah, ammonium has a Ka value, and it's right here, all right? So for if you put an acid in water, you want to use a Ka value, all right? But here's the problem. When you go to a textbook, you're never going to find a Ka value for a conjugate. You're never going to find Ka for ammonium, but you can calculate it, and I'll show you how. So let's just remind ourselves, what is the Kb expression for ammonia, a base, just a generic base? Nitrogen on ammonia grabs a proton, so you make NH4, the conjugate acid, and then what's the other product for a Kb expression? OH minus, perfect, all right. All right, so that's the Kb expression. Now let's write the Ka expression for the conjugate acid, so ammonium. So NH4 acting as an acid. Acids do what to protons? Donate them. So when we write the equation, we want to pop one of those H pluses off. So H plus is a product, but what else is a product? NH3, perfect, all right. So let's do some manipulation of K expressions, Hess's law type stuff. Add those two reactions up. Add them up. What cancels? NH3, anything else? NH4, and then what are we left over? What's left over? H2O, it's a liquid, equilibrium, H plus OH minus. Is that special? What is that? That's a K expression, specifically. Kw, because that's water, yes. This is the self-ionization of water, all right? So it looks like when we add up a Ka and a Kb for a conjugate acid-base pair, what comes out is Kw, okay? So when we add up with K expressions, this is midterm 2 review. When you add up two K expressions, right, what is the resulting K? How do we get the resulting K? How do we have to manipulate those K values for the two reactions we add up? Multiply them together. We don't add them, we multiply them. So that means that Kw is equal to Ka times Kb for an acid-base conjugate pair, right? So if I have a Ka expression for HF, right, has a Ka expression. F minus has a Kb value, and they are related by Kw. Right? This is really important because you'll only find for weak acids a Ka value, right? But we can infer what the Kb is if we're working with a conjugate base. Okay, all right, that's the big idea. Keep that in your back pocket. Honestly, if you get a tattoo to help yourself for the MCATs or whatever, that's a pretty good one. But of course, so Ka times Kb equals 1 times 10 to the negative 14. Again, I even wrote that only good at 25 degrees Celsius. Right? Ka times Kb is always equal to Kw, but Kw is equal to times 10 to the negative 14 at 25 degrees Celsius. Okay, so let's put it all together. This is what makes this chapter tricky, and it's identifying what am I working with, what K do I use, how do I calculate pH. Okay, HA is an acid. Do you agree? Yeah. So you want to use Ka to calculate its pH. Okay? So when you do your ice table, all right, and you solve for X, X is equal to the concentration of what if you use Ka? H plus, yes. So here's the thing. When we asked you to do pH calculations, you're going to do so many that you won't even need to do an ice table. Right? You'll see the trends come out. And you'll just know that when you use Ka, X is H plus concentration. All right, so HA is an acid, but A minus, is that an acid? No, it's a base. So should you use Ka? No, you need to use Kb, all right? But here's the thing, you will never find a Kb for A minus, an anion. So you'll need to calculate Kb using Kw over Ka. Ka will be given, but not Kb, so you have to calculate it, all right? So you're going to use the Kb expression. So when you solve for X, what is that concentration equal to? Concentration of what? If you use Kb. OH minus, yes, hydroxide, all right? So here are some examples. If I put HF in water, you'll go ahead and use that Ka value that's given, no problem. Okay? But if you put F minus in water, fluoride anion, you actually want to use the Kb, and that's calculated, right? This is acetic acid. If you put that in water, you just go ahead and use the Ka value that's given. But if you put acetate in water, acetate's a what? It's a base, so you need to use Kb. But will you find Kb of acetate? Nope, you calculate it using Kw over Ka. Ka is given, but not Kb. All right. Nitrous acid, that's an acid, so you use Ka. But if you put nitrite ion in water, that's going to be a base, so you have to use Kb. And that's the big idea, right? Acids tend to be easier, I don't know. So let's look at the bases. Same idea, all right? That for a base, you're given usually Kb. Okay, for a base, like if it was ammonia or whatever, we give you Kb. Okay, so when you solve for X with your ice table, what is that X equal to? Concentration of OH. How do you know that? Did you just do an ice table in your head really quick? No, what's the hint there? How do you know that X is hydroxide concentration? It's Kb, yeah, that's the trick. All right, okay, yeah, so B is a base, use Kb to calculate pH. Cool, all right. Is HB plus a base? Nope, it's the conjugate acid of the base. So if that's an acid, we have to use Ka to calculate the pH. But will you find the Ka of HB plus? No, you won't. You have to calculate it. Ka equals Kw over Kb. That Kb value will be given. All right, for completeness, when you solve for X, what is X equal to? Concentration of H plus, because what did you use? You used HA because it's an acid. And so X is H plus concentration. All right, so here are some examples. All right, here are some example bases. All of these will use which K expression? Kb. Kb. Will that be given in the question? Probably. Yes, it'll like 99% be given. But if I put NH4 plus in water, I don't use Kb. What do you use? Ka, but will the question give you Ka? Nope, you got to calculate it using the Kb that typically is given. All right. Here, what is this? Methylamine. All right. Methylamine, its conjugate acid is H3NH3 plus. Right? That's an acid. You got to use the Ka. And then the last one here, this is pyridine. All right. So again, squint your eyes. Look, there's nitrogens. If there's nitrogens, it's probably, if it's nitrogens and like hydrogens and carbons, it's probably a base. Pyridine is a base. But pyridinium with an extra hydrogen, proton, and overall positive charge, this is an acid. You have to use the Ka expression, which comes from Kw over Kb. All right. So what you see here is we have an acid-base conjugate pair and a base-acid conjugate pair. Those two values, the Kas and Kbs, they're related to one another by Kw. A constant. So mathematically, if Ka for the acid is a big number, Kb for the conjugate base has to be a small number. Versus if Ka is a really small number, it's a really crappy acid. What did we say earlier? Crappy acids have conjugate bases that are really good, that have really large Kb values. And so we see from this relationship that an acid where Ka is large, relatively large, the Kb for its conjugate is going to be a small number because both those numbers have to multiply to a constant. Versus if you have like a weak base that's really strong, you're going to have a really crappy conjugate acid. All right? And so that's the relationship between Ka and Kb. The bigger one is, the smaller the other one has to be. All right. Okay. So let's do a calculation. This is where things get hard, man. All right. Because we got to think about what is in our water, and it gets tricky. Okay, so this is a type 2. This is a maybe use the quadratic, but we'll probably just approximate. But we need to make sure we use the right equation. So here, we're calculating the pH of ammonium chloride. Like, you understand that it's going to be x squared over something, right? But we need to make sure we set that equal to the right K expression. So we need to ask ourselves, what did we put in the water? Ammonium chloride is a salt. So look at the salt, look at the cation, look at the anion, and ask yourselves these questions. All right? Ammonium chloride, if you look at the formula, if this was chapter 2 in 1210, you would recognize that ammonium chloride has a cation, NH4+, and it has an anion, chloride minus. We want to inspect those separately. Ask ourselves, is this acidic or basic or neutral? Is this acidic, basic, or neutral? And then that'll guide us in what we do next. So let's look at the two ions. So we have ammonium and we have chloride. Let's do the easy one first. Chloride, I'm just going to straight up tell you, is a pH neutral salt. Meaning if like for somehow you just had chloride ion in solution, this would be pH 7. So it doesn't contribute to H+ or hydroxide concentration at all. But what does contribute to your pH is the other thing. Because ammonium, the cation, is a what? What is it? It's an acid. How do you know it's an acid? It's the conjugate of a base ammonia. If you didn't know that ammonia was a base, there is a hint in this question. Where is it? I give you the Kb of ammonia, all right? But don't let this fool you, because a lot of students, they'll see, oh, Kb for ammonia, x squared over concentration equals Kb. But here's the thing. Did you put ammonia in water? Is that the thing you put in water? Nope. You put its conjugate acid in. You put in ammonium. So you can't assume that you just use Kb, right? So NH4 is an acid. So based upon these answers, what do we have to use? Ka or Kb? Ka, because ammonium is an acid. So let's do that. So let's write the reaction where ammonium is acting like an acid. What do acids do? They donate protons. So we donate a proton, and then what's left over? NH3. Perfect. So that's Ka. All All right, so Ka equals all those things. Let's do our ice table. All right, so initially we have 0.3 molarity of ammonium, 0 of everything else, minus X plus X plus X. So at equilibrium, we have 0.3 minus X of ammonium, X amount of H plus, X amount of ammonia. So Ka equals X squared over 0.3 minus X. Do I give you Ka in this question? Not quite. I give you Kb, but how are Ka and Kb related? By Kw. So I don't directly give you Ka, but we can solve it. It's Kw over Kb that is given. I do know those numbers. All right? So let me just put it all together now. So X squared over 0.3 minus X equals 1 times 10 to the negative 14 over the Kb that's given, 1.8 times 10 to the negative 5. All right, can you solve that? X, that requires the quadratic. Do you want to do the quadratic? No, so let's not. So we can go ahead and just get rid of that minus X. Doesn't that look exactly like we've been doing this entire class? X squared over initial concentration equals a K value. We just need to make sure we use the right one. Okay, so when we solve for this, X is equal to concentration of what? H plus, yes. You can tell from the ice table, or you can just use the trick. I used a Ka expression, so X is H plus. But if I used a Kb expression, X is hydroxide. All of these will always end up being X squared over initial concentration, but I want to show you why, and I show you the approximation. But we can do it because these K values are real small. Okay, times 0.3, there we go, square root. So I get that X is 1.3 times 10 to the negative 5 molarity, and you told me that is H plus concentration, so go ahead and negative log that and you get pH. All right, this is where asking yourself, what did I put in water? What did you put in water, an acid or a base? An acid. What's the pH you calculated? Acidic, so that matches. Here, where we start working with salts, it gets kind of weird and might not. And this is where mistakes can happen. Okay, so let's do 2 more and then we'll review. Because hopefully now we don't have to do an ice table. All right, let's calculate the pH of sodium cyanide. All right, so it's a salt. So split it up into the ions and ask yourself, what are those ions? All right, so sodium cyanide is composed of Na plus and Cn minus. So I'm just going to tell you that sodium plus is a pH neutral salt. All right, all group 1A and 2A metals, those are all pH neutral salts. All right, you put calcium 2 plus into water, pH neutral. Sodium plus, neutral. Potassium plus, neutral. There's some rules, we'll talk about it next class. But what's important here is Cn minus. What kind of substance is Cn minus? It's not an acid, it's a base. Yes. Here's the hint, all right? Cn minus is the conjugate base of HCN. HCN is a acid. How do you know? I give you a Ka value. Yes, I give you a Ka value of HCN, but that's not what we put in water. We put in its conjugate base. All right, so HCN is an acid, so its conjugate base is actually a base. So that means when I calculate the pH here, what K am I going to use? Kb. Did I give you Kb? No, but can we get it? Yes, it is equal to Kw over Ka. I know both of those numbers, right? Okay, can you, without writing an ice table, tell me the expression in terms of X? Can you tell me? X squared over what? 0.3. If you still feel uneasy about that, go ahead and make the ice table, make the approximation. You get X squared over initial concentration. So This is equal to 1 times 10 to the negative 14 over 4.9 times 10 to the negative 10. So when you solve for x, this should be simply a square-rooted thing. What is that concentration? Because this is tricky because I skipped doing the ice table because I got lazy. But you need to be, clever and understand that this x, so 0.00247 molarity, is the concentration of what? OH minus, yes, because you used Kb. So if you negative log that number, you don't get pH right away. You actually get POH. So let's go ahead and do that. Negative log of that number is 2.61. All right, and then you subtract from 14 and you get a pH of 11.4-ish. Okay, so let's check ourselves. Cn minus is a what? What did you put in water? It's a base. And the pH is acidic. It's basic. I don't know my brain. Yes, it's basic. 11 point whatever is basic. So that's all consistent. All right. One, last example. This time I'm not going to hold your hand. So tell me, you put this in water, is it acidic or basic? It's what? It's not basic. Acidic, yes, it is acidic. Okay, here's the trick, all right? It's pyridinium chloride. This looks a lot like ammonia. Also, look at this table. Do I give you the K value for pyridinium? No, I give you a Kb for pyridine. So pyridinium is the conjugate acid with an extra H plus on it, all right? So this is acidic, right? This is a weak acid, while chloride minus is pH neutral. So we can ignore that chloride. All right, so if pyridinium chloride is a weak acid, what K expression do I want to use? Ka. Did I give you Ka? Nope, I gave you A. This is a Kb. So we can simply get Ka by doing Kw over Kb. So I know those two values. Equals, do the ice table in your head. It's x squared over what? 0.1 molarity. All right, solve for x, and you get something, 1. So I'll do the whole thing. 1 times 10 to the negative 14 over 1.7 times 10 to the negative 9. Okay, 1e negative 14 divided by 1.7 e negative 9 times 0.1 square root. X equals 7.7 times 10 to the negative 4. Molarity of what? H plus. So when I negative log that, I go straight to pH. All right? And you get a pH of 3. That pH is what? Acidic. What did you put into water? An acid. Good. All right, so we'll stop right there and start doing some review for midterm, whatever. All right. So hopefully, us doing this pH work, pH calculations, we're still ice tables, still doing pH calculations. Really, honestly, us going further into chapter 16 helps us for midterm 2, actually applying these concepts that we're talking about. Okay. All right. So, go grab the document. We'll work through chapters 14 and I think we have enough time for 14 and 15. And then we'll leave the last part for Thursday. So midterm 2 covers the last bit of catalysis, so mechanisms kinetics. So it covers mechanisms and catalysis, our favorite sections. All of 15, so chemical equilibrium, and then pH calculations just for strong acids, strong bases in chapter 16, but also that relative acid-base table. Also, that is an important learning objective. So let's just go through this. All right. So here's a reaction. It's a 2-step mechanism. Tell me what the overall reaction is. So maybe tell me what cancels. A, C cancels, what else? C, perfect. So this overall reaction is A plus B arrow, AB. Perfect. Okay, so that's the overall reaction. So let's get the rate law. Is the rate law A times B? Nope. We actually have to look at the mechanism. We have to look at the rate determining step. That's the slowest step. The slowest step always determines our rate law. So rate equals K2 times AC concentration times B concentration. What's the matter with that? You can't have AC because that's an intermediate. You never actually add it to the reaction, all right? So we can't have that. So what we're gonna do is do a trick where we take the fast reaction and recognize that the forward rate, so rate constant in the forward direction, so A concentration times C concentration equals the reverse direction. So K negative. The K's really don't matter. They all just end up being 1K in the end. So what the relationship you see is that the concentration of AC is proportional to the concentrations of A times C multiplied together. So if you divide, both sides by K here, you see that AC concentration is equal to, again, K overall. I'm just combining the K's. A concentration, C concentration. And what I want to do is insert those known values into our rate law. So we see that our overall rate law becomes, again, some overall K times A times B times C. And that is our rate law, right? Where it's the two reactants plus the concentration of the catalyst seems to affect this overall rate as well. All right. Okay, so that is mechanisms. Rate determining step is the slow step. Get rid of intermediates by using fast steps. Okay, so let's inspect this reaction and look at the different components and identify, is it a intermediate, catalyst, or neither? So A, component A in this reaction is a what? Neither, because it is a reactant, yeah. But that's tricky, right? Because what? C is a what? A catalyst. But look, aren't both of them, they're both reactants, right? But what's the difference with C? It's consumed and then produced at the end, while A is just consumed. So that's what makes A a reactant, but C a catalyst. And then finally, AC is a what? Intermediate, perfect. All right, keep going. Okay, here we go. All right, so let's look at this reaction mechanism. This is a one-step mechanism, right here, what's drawn. Do you agree with this? This is one step. How do you know that this is one step? It's just one step, one hump, perfect. So we're inspecting the same reaction. A plus B goes to AB. So pretend we have the uncatalyzed reaction, that's one step. Let's say like there's just one step, it's slow. Here's the two-step mechanism that we just talked about. What is a property of catalysts? They tend to speed up reactions. So if I were to draw the two-step mechanism, would this be an appropriate reaction coordinate diagram for the catalyzed mechanism? No, what's wrong? But the activation energy is lower. That's one step. Yeah, so what should this look like? Two humps and also lower. Yeah, I just am making something up. So here we've lowered the activation energy for the forward direction, so it makes the reaction overall faster. But what also kind of changes here? What about the reverse direction? Did we change the activation energy for the reverse direction? We actually did, yeah. So if this was an equilibrium, we would lower both of those activation energies, and overall, we would see no net change. Catalysts do not affect chemical equilibria, but that's an idea here, that when we add a catalyst, we don't only lower the forward direction, but we also lower the reverse direction activation energies. Both directions speed up. All right, so with catalysts, activation energy is affected, but what is not affected with a catalyst? It's the enthalpy, or basically the energy change of products and reactants. See, we have A, B goes to C. Both of these reactions add up to the same overall reaction. So they both have the same enthalpy, where we start and where we begin, or begin and where we end. But what's different is, the steps we get to get there, right? So enthalpy is the exact same for both of these reactions. Basically, where we start, where we end. Okay. All right. So that is mechanisms. Let's talk about kinetics. Or sorry, no, that was kinetics. Let's talk about equilibrium. All right. Here's an equilibrium. It's an elementary reaction. Write the reaction. What are my reactants? A and B, and then it reacts to make C. Is that my equilibrium reaction? What's wrong with this equation? No equilibrium arrow, yes. So equilibrium arrow indicates that both the forward and reverse reactions occur. Okay. So KC expression here, assume everything's aqueous or whatever. It's going to be C concentration over A concentration over B concentration. See, now that we're like knee deep in acids and bases, this stuff looks easy now. Okay, all right, what else can we learn about this coordinate diagram? This reaction is what? Exothermic, how do we know? Goes downhill, perfect. Yes, that where you start and where you end up is lower. Okay, what else can we glean from this reaction? Okay, pretend we're at equilibrium, and what we're gonna do for the next couple slots is fill in with either alligator, like, greater than, equal to, less than things. So tell me, at equilibrium, how do the forward and reverse rates compare to one another? What do we think? At equilibrium. What's the definition of equilibrium? Forward rate equals the reverse rate. So the answer is they are equal to one another. What you are confusing with is rate constant. I didn't ask that. I didn't ask, how does the forward rate constant differ from the reverse rate constant? That's a different question. I just straight up asked, how does the forward and reverse, yeah, are you mad at me? Yeah. That's a different question. Okay, so let's get to that idea. Okay, so how does the activation energy differ? Okay, what is it? Which one's greater? Reverse. Yeah, so the hill is bigger when you go backwards. So now, compare the rate constants. Yes, now you can answer it, oh yeah, the forward direction is faster than the reverse direction in terms of rate constants. But at equilibrium, the overall rate of the forward is equal to the reverse. These two questions, they are different. So be very cognizant of that. If we're at equilibrium, the rate constants can be different, that's fine. But what can't be different is the overall rates. They are equal to one another. All right? Okay. And then lastly, what can you tell me about the relative amounts of products versus reactants at equilibrium? More which one? Products, yes, more products. Yes, because that's kind of like the low point. That's where they will accumulate. All right, so remember, there's two ways we can calculate equilibrium constant. What's the one we always do? Products over reactants. That's one way we can calculate equilibrium constant, but what's the other way? KF over KR. Forward rate constant over reverse rate constant. So based upon our answers we just got, whether which one you use, you'll get the same answer. K for this reaction is going to be what? A big number or a small number? Big number, yes, it's going to be a big number. I think the answer is A, greater than 1, yeah. Okay, because you're going to have a lot of products at equilibrium. Or you can think, yeah, the forward rate constant is going to be a lot faster. All right, okay, so let's do, I'm just going to keep going. Okay, all right, here we have a reaction, equilibrium. I give you K. Here are your equilibrium concentrations. What is C concentration at equilibrium? Okay, so I got this a lot in online homework in chapter 15. Like, yeah, we learned a new skill. We learned ice tables. But we don't always have to use an ice table. You only use an ice table when I give you initial concentrations, and you need to figure out how does the reaction have to adjust itself to get to equilibrium. But what's different about this question? We are already at equilibrium. So do we have to use an ice table? Nope, we already have the E line. And what's the trick with the E line? It goes straight into K. So these numbers go straight into K because we're already at equilibrium. Because what I got during like the online homework stuff is a lot of students, they saw these numbers and I don't know, they just would do a ice table and then they would do, oh yeah, minus 2x, minus x plus x, when they really didn't have to. These are equilibrium concentrations. We already have the E line, so you don't have to do all of that. So at this point, see that Kc is equal to C concentration squared over A concentration squared, B concentration. So at this point, you know everything, and you just solve for C. And so I'll just call that x. So 100 equals x squared over 0.4 squared 0.1. And I think if I remember this, I don't know, I already forget. 100 times 0.4 squared times 0.1 square root. I get that x equals 1.3 molarity. And since this is Kc, molarity is A-OK. Right? X in this case is concentration of C at equilibrium. Right? And so the idea here, all of these are equilibrium concentrations. Just go ahead and plug those in to the K expression. No ice table needed. To check yourself, all right, just plug those numbers, all these equilibrium concentrations back into K. Just plug them all back in, and you should get 100 come back out. If you do 1.3 squared over 0.4 squared times 0.1, you should get 100, hopefully. All right? Okay. All right, so let's do, yeah, we have time for this one. Okay, so now we have this one, a different equilibrium. We have 2 molarity of C initially in a 4-liter container. After equilibrium is reached, we measure 0.4 moles of A. What is Kc? So, do we need an ice table here? Yes, because I gave you initial conditions. We need to figure out equilibrium conditions. So here, initially is the key word. So let's do the ice table. Okay, so we're calculating Kc, so what should our unit in our ice table be? Molarity. I give you 2 molarity of C, so that should be 2 molarity. How much A and B do I have? 0. So this reaction has to go in reverse. So minus 2x plus x plus x. I don't have to reverse the reaction. In fact, I don't actually have to flip it or anything. I use the change line to account for it going backwards. So at equilibrium, I have x amount of A and B, and then 2 minus 2x of C. All right. How am I going to use this 0.4 moles of A? What is that? That's part of the equilibrium line, yeah. So here, I'm giving you a hint at the equilibrium line so you can fill in the rest. But here's the thing. I asked you, what is the unit in the ice table? Molarity. What is this unit? Mole. So is x 0.4? No, it's not. What is x? It's actually 0.1. So here, x is, concentration of A at equilibrium, but it's concentration. So it's 0.4 over 4 liters. So x is actually 0.1 molarity. All right? So after you get that detail, and that detail is very important or you'll be wrong, x is equal to 0.1. So 0.1 molarity, that's A. What is B concentration at equilibrium? Also 0.1 molarity, perfect. And then what is C? Should I make an approximation and just say C is 2? Nope, because you literally know what x is and can calculate that it's 1.8. Right? And so when you plug all those things in to get Kc, it's equal to 1.8 squared over 0.1 squared, and I think it's like 370 or something is Kc, if I remember correctly. So that K value is what? Big. So you should see a lot of what at equilibrium? Products. Is that what you see? Yes. Okay. I have 1 minute, but I think we can do these ones fairly quickly. Okay. Consider this reaction. Look closely at the states. How will the equilibrium shift if we add C, which is a gas. It goes, tell me forward or reverse? Reverse, yes. What if we add B? No change, yeah. What's the difference with B? It's a solid. What if we remove A? No change, perfect. What if we neutralize some C? It goes forward. Neutralize into something else essentially means we removed it from the reaction, right? Okay, what if we squeeze on the container? Which way does it go? Reverse, to the side with no moles of gas. Versus if we increase the size of our container, it moves forward, where we can make more moles of gas, we can buy more plants for our big house. All right? Best of luck. Oh, remember my review session tonight? Yeah.